Welcome to Data Skeptic. Data Skeptic brings you discussions about how data is changing our world. Our interviews are conversations with thought leaders in topics like data science, machine learning, and artificial intelligence.
When we get the timing of things right on Data Skeptic, we introduce mini episodes strategically so that listeners that follow in chronological order have some background that's appropriate for enjoying our interviews. In today's interview, my guest Dongho Kim and I touch on a few advanced topics. If you're a more experienced listener and you want to skip forward to the interview, feel free to do that now. For the rest of us, I thought I'd do a small pre-game show and prep some details for listeners. Broadly speaking, in this interview we discussed the field of multi-agent systems. This is a class of problems and solution techniques for situations in which autonomous agents are operating in the same environment. This includes simple games like tic-tac-toe. It's a 9x9 grid, that's the environment. There's two players, each taking actions and observing the actions of the other. Multi-agent systems also applies to complex things like, let's say, local delivery restaurants competing with each other. In multi-agent systems, there are two or more agents all acting independently of one another. Each agent has the desire of behaving optimally, although exactly what we mean by that varies a bit across approaches. Depending on whether you can influence all of the agents like a team, or control only one agent will be an important deciding factor in what methodology you use. Some approaches are centralized. Each dumb agent reports updates to some master control unit, which in turn gives them new instructions to follow. There's a lot of appealing things about that approach, but it usually turns out to be pretty impractical, or not applicable to the problems at hand. A more widely useful approach is to treat the problem as a decentralized decision-making process. Each agent is autonomous, and should have the ability to learn from experience and formulate their own decisions without the input of some external source, or maybe just not the consistent input of that external source. Dongho and I discussed some of the techniques used at his company Prowler.io. They're working on a platform to help tackle these decision problems and specify the agent's function. Put more in the vernacular, each agent has to figure out how to behave. Remember that there are other agents involved. Multi-agent systems problems are interesting when the agents must account for each other's behavior. Are the agents going to cooperate or compete with each other? Like most interesting questions, the answer is, it depends. Perfectly rational agents are neither competitive nor cooperative by nature. Their behavior is a consequence of the game they're playing. Each player has to pick their own strategy, and depending on the choices of each agent in how they are going to behave, the agents might end up helping, opposing, or ignoring one another. The field of game theory comes into play here. We'll do a mini episode on game theory in a few weeks to go into more detail, but the basic idea is that game theorists care about strategies that are in equilibria with one another. In the case of two agents, an equilibria is a pair of strategies. Each agent has their own strategy. They could be identical or they could be different. And so long as both agents stick to the plan, everything is copacetic. Neither agent has any motivation to change. In fact, changing their strategy, while the other agent sticks to the original strategy, would actually be harmful. That's the core idea. Once in equilibria, it would be suboptimal to leave it. This is a nice approach in many ways. All of the quote-unquote difficult stuff is handled up front, computing that equilibria. That can often be hard. But once you've got it, typically following it is quite easy. However, there are some problems with equilibria-based approaches. There exist problems for which there aren't known equilibria solutions. There are other problems where we know the algorithm to find the equilibria, but the algorithm is inefficient or intractable, and therefore of no real use to us. Furthermore, many scenarios have multiple equilibria, and there's no obvious way for agents to synchronize on the best one. This is often called the non-uniqueness problem, because for a given game, there's not necessarily a unique best solution. Lastly, should any of the agents start to ignore the equilibria? Maybe they don't know about it, or maybe they're irrational. The agent that's stuck to the plan, that is the equilibria strategy, that strategy does not specify how they should behave in this off-equilibria behavior. This is commonly called the incompleteness problem, because in most games, the equilibria strategy doesn't say anything about how to behave if other players aren't also playing the equilibria approach. So if you deal with perfectly rational agents who have common knowledge of perfect rationality, then absolutely, you should use an equilibria-based solution. But if there's a chance you're facing someone of bounded rationality, or frankly, an irrational person, then game theoretic approaches might not be for you. Decision theoretic approaches are a good alternative to game theoretic ones when one or more of these objections I mention is relevant to your problem. However, decision theoretic approaches are not without issues themselves. Most notably, they typically suffer from the curse of dimensionality, which I seem to be mentioning quite often on the podcast and on the dataskeptic.com blog these days. For a quick refresher, the curse of dimensionality is the problem that as you think about the future and what you might do and how someone might respond to that, and again, you form this tree-like structure that's ever expanding, and to search the whole space to its leaves to find the optimal solution gets impractical very quickly. You'll need to have some technique of pruning that tree in some way. The curse of dimensionality makes exact solutions to most decision theoretic approaches infeasible. Alternative options include finite horizon approaches, where you only think a certain number of steps ahead, and other approximation techniques like discounting, or using something like a particle filter to approximate your beliefs. Independent of the game theoretic and decision theoretic ideas, another important concept in agent-based decision-making is the idea of bounded rationality. We'll go into this in more detail during the episode, but essentially, bounded rationality is when we try to model the decision-making process of agents that do not have infinite computational resources, memory, and time. In other words, bounded rationality seems to be the way to go if we want to talk more precisely about how agents behave in the real world. Incidentally, bounded rationality is why I personally avoid shopping at stores where the price is not clear and negotiation is the norm. I really dislike that. I mean, sure, you need to negotiate on big things, the purchase of a home or buying a business or something like that. I absolutely get it there. But if I want to buy an apple, I just want to know the price of the apple. When merchants keep that information secret, it's almost like saying, oh, you have to come to me now and we're going to engage in something. And to behave optimally in those situations, one has to dedicate time and energy to computing the ideal strategy. While I do have an interest in these methodologies, I have no interest in applying them to casual shopping. In other words, I don't want to have to think about it. I'm thinking about something else. And that makes me boundedly rational. I have to arrive at my choice and get it as optimal as I can get it, using only the brain that's in my head and any tools around me. Bounded rationality has always been an important concept in artificial intelligence, but it's also showing up in other areas of data science now as well. Streaming systems are a great example. When streaming a large amount of data, and presumably needing to handle it in near real time, one has to find an implementation that works well on the fly, in real time, and with limited computational resources. Things like probabilistic data structures, the hyperlog and the Bloom filter, are great examples of this. Okay, 3 more quick bullets from my notes before we begin the interview. A quick one first. I mentioned the idea of the trembling hand. This is a notion in the literature to describe boundedly rational agents. A perfectly rational agent with infinite resources should be able to compute an optimal policy in any given situation. They should be the master strategist of whatever problem they face. A boundedly rational agent should be able to compute something close to the optimal policy, but in which they occasionally make suboptimal choices. If somehow you already know the optimal action your opponent should take, you might want to model their next action as a probability distribution over the actions they will take. Naturally, selecting the optimal action is probably the most likely one, but with some probability, your opponent is going to make a suboptimal action, and that's almost like the trembling of their hand as they go to hit the button and accidentally hit a button close to it to select their action. Something along those lines, I would guess, is the origin. But in any event, trembling hand simply means that we assume the agents we interact with are pretty much rational and typically make the rational choice, but with some probability we'll maybe make the second best choice from time to time, and with even less probability the third best choice, and so on and so forth. Next note. Gaussian process is mentioned briefly in passing. It's an important topic in and of itself. Frankly, I'm a little embarrassed that Data Skeptic has been going since 2014 and we haven't gotten around to covering Gaussian process yet. We will get to it eventually. For the sake of this interview, if you simply know that it's basically a regression technique, that's enough for you to enjoy our conversation today. Lastly, Dongpo mentions information theoretic approaches. Let's first define information theory. It's the study of how one encodes information. For example, the best path to drive a car between 2 locations can be encoded as a series of left and right turn instructions. And I guess also go straight at some intersections, but let's keep it binary just to make it easy. The simpler the path, the fewer bits of information required to convey the journey to another person. Agents that are communicating with one another often have a limited channel for sharing information. This could be due to bandwidth or time or anything like that. So information theory can be applied to many aspects of multi-agent systems and optimal decision-making. When one says information theoretic approaches, I think the most general definition is to say that the approach somehow involves the mathematics of information theory. The specifics on how it does that can vary, so I won't get into that here. All right, without further ado, let's jump right into the interview.
My name is Dongho Kim from Prowler.io.
Tell me a little bit about what Prowler.io does.
So basically, we are building a platform for autonomous decision making so that you can easily model your real environment, very complicated environment using historical data. And on top of that, we are optimizing millions of micro actions or decisions from, again, millions of different agents or decision makers in that environment. So that's what we're doing at the moment.
Makes sense.
Yeah.
So when I think of a large group of autonomous agents, it could be, fleets of self-driving cars.
Yes.
Could be video game characters.
Yes. Exactly.
What are the kinds of areas you tend to work on?
Well, even though our technologies are quite generic, so it could be applied to many different realistic problems, but at the moment we are focusing on, firstly, video games industry, and some smart city applications, including ride-sharing applications. And lastly, we are also looking into a bit of financial applications for portfolio optimization or stock trading, that kind of things as well. From the video games perspective, when we say that we don't need a superhuman player, we just want to maximize the engagement, we believe that the understanding of human behavior is really crucial there. Human players don't behave perfectly or optimally in games, right? More specifically, we've been interested in the notion of bounded rationality as well. So why the humans are making this kind of decisions. Yeah.
Interesting. Yeah, for any listeners who don't know, could you elaborate on what bounded rationality is?
Even though there are many different ways of defining bounded rationality, like computationally, human brains can be limited to make that kind of massive computations. Or there can be some limitation of the long-term planning. So like people don't behave looking forward to like up to one year later or something, right?
Yeah.
So, and that's another source of bounded rationality. So like while doing the optimizing the decision making, we wanted to bound computationally or from the other aspect, like even though the decision making or behavior is not perfectly optimal, but in general, there are some problems where having the kind of limited rationality is better. So there's video games, it would be one of the place we need slightly worse intelligence.
I don't want to play AlphaGo.
Yeah, exactly. Yeah, exactly. So the question is, how can we model that kind of limited rationality? So this was question. We have used some information theoretic approaches to model the kind of relations between the optimal behavior and the imperfect behavior and that kind of thing.
Oh, interesting.
Yeah.
So the naive approach, in my opinion, is just finite horizon planning. You restrict the computer player from looking more than n steps ahead.
Yeah.
That works okay.
Yeah.
What advantages do you get with the information theoretic approach?
So the advantage was that we can easily tune the behavior of AI agents. So we could have just only one single parameter or a single dial. If you increase the value of parameter, and then it would behave optimally. But if you decrease the parameter value, it's gonna be imperfect behavior. So it's really easy to tune.
Oh, interesting. So is it that you can compute the optimal solution and at one end of the dial always execute it, but at lower ends, like trembling hand, you make errors?
Yeah.
Oh, very interesting.
Yeah.
So let's go into some of the methodologies you use. Multi-agent systems have a variety of different approaches, and many of them kind of blend together. We're now having, some reinforcement learning and some deep learning and some Bayesian stuff all going together.
Yes.
What are the approaches you have found the most use?
Yeah. So we are marketing ourselves as a principled AI company. Well, even though it's gonna be a little bit, arguable name, but we think we are principled in the sense that all the decision making should be based on the very strong principled, mathematically principled probabilistic models. So which means that we're mainly interested in the use of Bayesian approaches rather than deep learning technology because of many advantages of Bayesian models. So it's fully probabilistic and it's interpretable, which means that you can understand what's going on behind the scene. And also in terms of decision making, you can be easily risk aversive, just not optimizing one objective. So like in many realistic scenarios where AI's decision making could be easily risky or even like can cause some catastrophic events, right? So like to be able to mitigate that kind of problems we can expect. So we're more focused on Bayesian models, more specifically Gaussian processes.
Ah, really? Okay, makes sense. So one of the challenges I'm aware of in approaching a multi-agent problem is that you have to do a really good job figuring out what the actual problem is.
Yes.
You know, the agents, they may be cooperative, they may be in competition, they may be cooperative and do things that look like competition if you don't ask them to do the right things.
Yes.
What are some of the challenges you face in defining the problem?
Yeah, so the people can easily imagine that the multi-agent decision-making could be much more computationally expensive, like normally like exponentially expensive because according to the number of agents there, right? So obviously we need many different approximation techniques for that. Computationally, we might want to distribute all the computations of each agent by having some communication channels between agents so that we don't have one centric decision-making component for a fleet of agents. So that's the one way.
So when it comes to distributing that, what we call them autonomous agents, they need to have autonomy. We can't centralize and then develop a policy and hand it out to everyone. They've got to independently do some compute.
Yep.
And that's also nice because it means, it's highly parallelizable.
Yeah.
But as you mentioned, now they need to communicate, which is a new problem. Can you talk a little bit about some of the challenges you face in, I guess it would be coordination, essentially, how they share information?
Yeah, I think it's a very good question. I'm not an expert in multi-agent learning, so maybe I'm not the best person to answer the questions. But in general, like even though we have only a very limited communication channel between agents, like I believe we have a good understanding how to deal with that kind of limited information channel to optimize the entire goal of different agents and something like that.
So I'd love to get a little bit into Prowler and what you guys do. I can't claim I for sure know the entire landscape of platforms that will enable people to do multi-agent systems, but I'm not aware of too many. In fact, when it comes to something like a POMDP, as far as I know, state-of-the-art is still Anthony Cassandra's problem solver from the early 90s.
Yeah.
There aren't a whole lot of great tools the way like sklearn is a great tool for sort of typical supervised learning.
Yes.
Can you talk about, was that the motivation, or are there other things I'm not accounting for in building a platform?
The motivation of that platform is obviously because our technology is generic, so we wanted to have a platform for serving different use cases from different industry verticals, right? Like even though many researchers are still solving, just in case of POMDP actually, like because the problem is really notoriously hard to solve actually. Many researchers are still focusing on the laboratory type of toy problems.
Right.
But you can't really imagine any other scenarios where we have only one decision maker. This kind of combination of three different communities, such as probabilistic model and the reinforcement learning and the game theory, don't talk each other in the universities, for example. So it's really hard to communicate with the people from different research communities. While building a platform, we thought that kind of combination is really unique, and we haven't seen any kind of that kind of combination yet in any other companies. The building a platform and applying some ideas to real problems actually excite many researchers and professors we hired so far, because like we can finally close the loop with some really interesting applications. So that was sort of motivation, I guess. Yeah.
So when it comes to the platform, what do I tangibly get? Is it a software library I use? Is it something I log into and it's an interface and everything? What is the Prowler.io platform? Are you considering an advanced degree? How would a Master of Science in Business Analytics advance your career? The Mendoza College of Business at the University of Notre Dame has a program that can be completed in as quickly as 12 months. Downtown Chicago classes take place on Fridays and Saturdays. This program will teach you to make strategic business decisions based on data, not on anecdotes. To data skeptic listeners, that might sound like an obvious statement, but let me tell you, the business world isn't always as data-driven as it should be. That's why we need more data-driven professionals. Find out if the Masters of Science in Business Analytics could help you be one of those thought leaders. Visit mendoza.nd.edu/dataskeptic. What is the Prowler.io platform?
Yeah, we are also working on some pilot and UX interface projects as well. I think this kind of platform should be really easily usable even to the non-experts of machine learning and reinforcement learning. With some nice interface, people shouldn't be bothered with complicated hyperparameter optimization and different things, right? So it's still quite hard to predict because we believe that our technology would be much more sample efficient than any existing technologies. So with a handful of training data, you will be able to visualize easily what's going on in your real environment probabilistically, and then see how the agents communicate with each other to optimize their decision making.
So maybe we could frame it in the context of one of the examples you gave, that of ride sharing. So there's a fleet of vehicles. They're all autonomous, but they, I guess, have some communication channels either with each other or with some central distributor kind of person. The objective is presumably to maybe minimize the wait time or something along those lines. It's probably a little bit more complicated, but just stick with that one maybe for discussion's sake. We can represent each vehicle and we know the environment, which is the street system, although it's probabilistic because you don't necessarily know about traffic and stuff like that. How do I take all those things into account? How do I get them into your platform? And then how does the platform transform that into a solution?
To answer the question, maybe we need to start from the probabilistic model for that first. We originally start from the real data of taxi demands, where each point represents a taxi passenger, the real demand for taxi. And that we were able to model very nicely the kind of data which has a temporal spatial relationships. So like it's basically it's on the two-dimensional city map. And also, there is a clear dependency along with the time horizon, right? So we applied a Gaussian process model very nicely. So we can easily predict, for example, tonight, like around 6 p.m., maybe there will be this kind of taxi demand over the city map. On top of that, now we need to optimize the decisions of fleet management. Firstly, what we're doing is that we call it demand matching. We view the fleet of taxi as another probability distribution. So what we are going to do is that to match those two different distributions from one the supply and one from demand. The optimization objective could be formulated as a K divergence between two probability distributions. And then after matching those two distributions, we need to assign tasks to each taxi driver, for example. That can be also done with some techniques. The important bit is that while matching those demand and supply, we should act proactively because we do have a predictive model. The fleet of taxi proactively move to the high demand area to reduce the waiting time of passengers and that kind of thing.
Gotcha. And that decision, that policy, if you will, that someone should go from low to high demand, if everyone does it, it'll oscillate, back and forth. You'll get everybody in dense clusters and then they'll move back out. Do you have to control for that in any way?
Yeah, we can definitely control that. We can easily say that the optimal configuration of a fleet of taxi. So while presumably by communicating with each other, the other drivers, it could be easy to do a centralized planning on top of that. So we obviously started from there. Yeah, but we are also looking into this, that kind of distributed scenario as well.
Interesting. So what advantages do I get by going from a centralized to a distributed system?
The first problem is obviously the computational complexity of centralized planning. Because of the combination of different actions from multiple agents, is normally very hard to solve. So by formulating the problem as a distributed problem, it's computationally easier. And also in terms of reliability, it's again better. Just for example, if we have just one central place, we make all decisions. If that doesn't work, it's gonna be broken.
The whole system.
Yeah, the whole system will be broken. So in that sense, it's also this advantage of distributed.
Makes sense.
Yeah.
And I could imagine where if I were a shared car pilot and I was in the north part of the city, I care about the cars near me, but I probably don't care about what's going on in the south of the city at the moment.
Yeah.
How do each individual agents then compute their policy? Do they have a local piece of technology that tells them routes to take? What's the process?
Presumably, some central system or the fleet manager can direct or guide you to move to a certain part of city, for example. But it's not always easy, right? We need to carefully design that problem as well. So how can we incentivize the drivers to move there, rather than just direct micromanage all drivers? So that's where the game theory comes in. We've been very interested in the mechanism design. So how to design this kind of fleet management so that we can easily, gently, guide taxi drivers, not just, bothering them.
Yeah, let's unpack the game theoretic aspects. To my understanding, something is game theory when the solution's in equilibria, that all the agents have no motivation to not follow the plan.
Yeah.
So how do we come up with such a plan that's convincing to all the agents?
I think that question still relates to the mechanism design. Yeah. So if I understood that question correctly, it's going to be really important to satisfy the drivers as well, so not just passengers, right? So giving a proper incentive to drivers would be a key aspect of this system as well.
So are you saying that perhaps if there's, from the Gaussian process model, there's some area that's significantly underserved and it's not sorting itself out, that we might pay a bonus of some kind for drivers to go there?
Exactly, yeah.
Oh, very neat.
Yeah.
And you'd also mentioned there's some reinforcement learning involved. Does that show up in this application too?
Yes. So in the case of reinforcement learning, we're mainly looking into the use cases for video games industry. So people so far they're trying to solve complex video games or like the game of Go, the kind of really, really challenging problems. But from the company or game developers' perspective, the question is how to make those games more fun, or like how to make game players more engaged. Right? That's the question. While solving the conventional game problem, but not just solving that game perfectly, like the superhuman AI agent in that video games, we were more interested in the more like for example, human-like AI players there, which you can't really discriminate between the human players and AI players. That's one of our goals.
Oh, very interesting. Yeah. Sort of a Turing test for video games.
It could be, yes, it could be. Yeah.
In terms of getting back to the platform then, let's say I'm someone with a multi-agent problem and I have a pretty well-defined idea about it. I know my state space, even if it's partially observable. I know the function that describes its partial observability. I know how the state transitions, and I know the reward function I want to use. What I don't know is how I'm going to scale this up and deal with the cursive dimensionality.
Yes.
Is that when I would come to Prowler.io?
Yeah, that's again very good question. In POMDP problems, as you mentioned, even though we have a full models for partial observability and the state transition, everything is still quite challenging to solve it, right? Because of those problems, even with approximate algorithms for POMDP, it's still challenging to solve the current problems. Rather than do planning completely, considering all the uncertainties you could see, we presumably uncover a bit of uncertainties from observation using probabilistic models and use those uncertainty, part of uncertainty to be able to do a long-term planning there. And that would be the way to handle this. I'm not sure I'm answering this question properly, but like the conventional POMDP algorithm is slightly different from the reinforcement learning the approaches, right? So the key property in POMDP algorithms is actually having that model of partial or uncertain observability. And then how to utilize that knowledge in your long-term planning. In general, the partially observable reinforcement learning problems, we don't do that. So I think we are going that way as well to have a better algorithm for decision making under uncertainty. But it's very challenging problem yet. So yeah, we are working on that. Yeah.
So in the supervised machine learning world, it seems like developers of tools have centralized on pretty nice API. We have whatever library you want. You have a fit method and a predict method. And it's pretty much there everywhere. How you do the various nuances of each algorithm is a little different, but it's pretty uniform. And it can be because supervised learning is sort of solving the same problem, right? Labeled data to what's the underlying data generative process.
Yes.
In a lot of the problems we've been discussing, there's more heterogeneity. There's different types of problems. Sometimes it's equilibria-based, sometimes it's just reinforcement learning-based. So it seems your problem is a little bit more challenging in the variety you can face.
Yes.
How can you go about coming up with approaches and tools that work in video games and in car sharing and maybe autonomous drones flying around as well?
For smart city applications, we mainly need a temporal spatial model. And for other type of applications, like if we do care about just not the two-dimensional spatial data, so if this is sequence data or decision making, and we're going to use slightly different Gaussian process model for that. So slightly different in terms of probabilistic model, I guess. But in general, we've been thinking that with those two kinds of model, there are lots of different problems we can solve. And on top of that model, decision-making perspective, also there are lots of varieties in decision-making in terms of number of agents and the many different perspectives. But so far, we didn't see that challenges in that sense yet. Yeah.
Gotcha.
Yeah.
So where have you seen the most interest in your work? Is it clients coming in who want to work with you or machine learning people who want to use your tools? What's been to date, the areas of interest?
Actually, we are interested in both. Actually, we've been planning to open up one of our probabilistic model for the study of transportation or smart city scenarios as well. But hopefully, the customers or partners from industry will be able to use our platform for their complex problem as well, hopefully.
Very cool.
Yeah.
Well, if people want to keep up with what's going on with the platform, what's the best place for them to go to learn the news and follow along?
It could be our website. So we do have many blog posts about our recent research and also the interesting story about our platform as well. So
excellent.
Please visit our website.
Well, I'll have that in the show notes for people to check out.
Yeah.
Thanks so much again for joining me today.
Thank you so much. Thank you.
I know that many of you now go on Mondays to dataskeptic.com to check out our feature of the week. We've been having a lot of great fun doing that, and I appreciate all the feedback we've gotten on various things we've posted. We try to do one interesting thing a week, and we also send that in our email newsletter, so sign up for that, and you'll get not spam, but just one kind of cool thing every week. We've been doing a lot of work at dataskeptic.com recently, and there's one feature we quietly launched that a few of you discovered this week. If you go to the Contact Us section, there's now an area where you can leave a listener question in the form of an audio clip. I'm about to play one, so thanks to Sid, one of the first people who did that, and we're going to answer his question here today.
How can I spot opportunities to apply AI in my organization, and what can possibly go wrong?
So as for spotting opportunities to apply AI in your organization, the first thing that comes to mind is a bit of wisdom I'd heard Andrew Ng say at some point. His basic heuristic was that if there's something that a product manager can do in about 1 second, in the same way that we can do image recognition, human beings can in about a second, or tell if a word is misspelled, or things like that. If a human can do the task in a second, then it's very likely that machine learning can solve that problem for us. So I do think that's a surprisingly good heuristic, seeing as how it's not formal or rigorous in any way, just a rule of thumb, but quite a good one actually. Even still, many applications that are appropriate to label artificial intelligence are truly moonshots. They're hard to sell to leadership. Hey, Mr. Boss and Mrs. Executive, can we please have, 6 months of all our facilities, servers, and the team, and we want to conduct an experiment and build something, and we're not quite sure if it's going to work or not. Well, I don't know if you're going to get permission to do something like that. There have been some organizations who have taken moonshot initiatives like that and done extremely well. But for every success featured in a magazine somewhere, there's dozens or hundreds of failed organizations that no one really talks about. The other rule of thumb I would recommend is to ask yourself if your idea can be considered a variation on a theme. If you find out that some pizza delivery company is using computer vision to count the number of toppings, I mean, I don't know why that would be that useful, but I'm sure one could do it. In fact, that's my example. If I were hired by a pizza company and they asked me to build that, I could pretty much guarantee it's possible because I've seen other applications that do similar things and I know I can transfer that. Either, figuratively in the sense that the same methodologies will apply, or maybe literally in the sense that I'll apply transfer learning. So feasibility is really the first hurdle to cover. Can you be sure that your great new idea, which is probably novel and innovative if we're going to call it artificial intelligence, is it actually going to work? Next, of course, is, well, how long will it take? But I'm of the opinion that it's not useful to estimate those things in terms of, year-plus plans until you've at least done some exploratory analysis. Take a month and see how far you get, and you'll be informed enough then to maybe make an appropriate roadmap. But the other bit of advice I want to give you is to ask, does the initiative, if successful, reduce a major operational issue, like a manual process? If you want to apply AI, it really needs to be a game changer. Not just because of the cost to build something, but because it has to really capture the attention of the organization. If it doesn't solve a critical issue, or if the decision makers fail to see the value of the solution you've brought to them, it's not going to go anywhere. So any way you plan to apply AI in an organization really needs to be game-changing to justify itself. That is, if you're going to build something. If you can leverage many of the API services coming on the market that do a lot of this stuff for, very little to no cost, facial recognition being a great example, well, then your ceiling is a little lower. So go back to that rule. Can this reduce some operational process, either in terms of cost or time to delivery? Can it get rid of a manual step? Now, that's not always an easy question to answer. I try to break the work down into very atomic level steps, almost to write the pseudocode of a person's job description. Then I look at each of my steps and I say, well, do any of these tasks require more than 1 hour? And the answer invariably on the first pass is almost always. So that means it's time to break it down again. Break it down into these unit tasks where it becomes very mechanical. Now, you might not finish this process. I don't know that I could really describe what I do in these unit tasks that read like, some very simple instruction manual. But in your quest to do that, you'll be asking a lot of great questions along the way. And as you ask those questions, you're likely to spot opportunities. Oftentimes on a journey like that, what you'll find is that some important role in the organization, maybe a role that has many people filling it, there'll be a reluctance to implementing anything in AI, with the thought that, no machine could do my job, and that may or may not be true, but surely some machine can do a part of that job that the person finds annoying, and maybe it can do it very well. Maybe you can set it up to a resistant person in such a way where it's just going to make them a suggestion, and if they like it, they can quickly accept it. If they don't, they can reject it and make their own choice. Now, of course, after that, you can start to track the accuracy of the decision-making process they're making, but that's an aside. So in summary, I'd say use Ng's heuristic, think long and hard about plausibility, think harder about impact to the organization to justify it, and then start breaking down your business function into very atomic steps, and ask yourself which ones would be useful to automate and which ones seem plausible to automate. I'd say that's how you spot opportunities. Now, the second part of your question was, what could go wrong? Well, the obvious thing is big investment, no results. And I'm hearing more and more that that's the unfortunate circumstances a lot of companies find themselves in when they look to AI for solutions for their business. But if you're a smart data scientist trying to bring techniques in-house and promote innovation in your organization, hopefully you can avoid that path. Well, what else could go wrong? Well, you could have a nice result, but one that's not good enough for the business to roll out. Perhaps your classifier is 88% accuracy, but for whatever reason, the business can't tolerate anything less than 95%. Can you get it there? Well, it might be uncertain. What else could go wrong? Well, could the artificial intelligence-based solution hurt someone? Or more specifically, could it hurt someone in a meaningful way? If again, you go to, order a pizza and something about the website prevents the user from buying the pizza, I don't think they're going to starve. In fact, they'll probably just go to your competitor. And while, of course, no one wants that, I think the, threshold for having sort of some HIPAA-compliant thing in place here is pretty low. A mistake at pizza delivery using AI techniques is more likely to hurt the business than the consumer. So analyze your specific use case. And I know many of you have more sensitive use cases, hospital settings, even military perhaps. These are areas where people can become hurt, and that's absolutely what could go wrong. Now, within all this, a lot of people will say, well, unemployment is what could go wrong. How do you know this solution won't put a great deal of people out of a job? And while from time to time things like that can happen, I personally find that to be largely alarmism. Most applications of artificial intelligence to date, and I think in the short term into the future, maybe even into the long term, are really more about efficiency. 80% of customer service requests are very simple. How do I reset my password? What's my username? If you have that problem, what do you want? A fast answer. An algorithm will always be faster than a person. Now, some people demand to speak to a human, whether they need to or not. Okay, if we can automate 80% of the requests, even if we promise, people who don't want to talk to some sort of chatbot, they go straight through to a live person, you've just made that staff much more efficient. And maybe that wait time of 45 minutes can be cut to 4.5 minutes. That automation could make more efficient use of the staff's time and thus allow them to deliver a higher quality of service. Oh, but the company will make cutbacks and then we'll be all waiting 45 minutes again. Well, if that's the case, then vote with your feet. Find an alternative vendor who doesn't do that and go to them. Companies are optimizing for revenue, and if you're the one giving them money, then you have a say in the matter. Stop powering the machine if it's malfunctioning. So could AI unemployment really be all gloom and doom? I'll give you a maybe on that. I don't know, truly. And that's the point. No one does. How many out-of-work typewriter repairmen do you know? Anybody? Nobody knows an out-of-work typewriter repair person. Does that mean that they're all still working? They all still have jobs? No. It's because they all found new employment between now and then. Now, I'm not going to say that wasn't hard on people. I understand that better than you might think. But economics is complicated. Anybody that tells you they know for sure how something like self-driving cars is precisely going to change the world, ask them for an explicit statement of their claim and what evidence they have of it beyond their gut instinct. All of us are guessing about what the future is going to look like, and hopefully at least one of us is going to guess correctly. But I doubt we will know exactly which one of us guessed so correctly until it's already happened. AI safety is an important issue. Weapons and warfare and AI are issues that, regardless of one's perspective on the matter, are certainly worth debate and good rhetoric. But Sid asked about opportunities in his organization. I think for that, with what we'll be able to do with AI in the next 5 years, there are a limited number of organizations that really need to worry about safety and harm. Those that do should be. But I think it's more likely what'll go wrong is, as I said to begin with, big investment, no results. The only cure for that is good communication, a solid plan, and a lot of built-in steps about go forward or don't go forward. Great question, Sid. Thanks so much for this. If you guys enjoy the question format, please let me know. You can leave your questions at dataskeptic.com and click on Contact Us and go down to the listener question area. I hope to hear from more of you this week.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.